Good afternoon. Thank you guys for being here. I am well aware that I am one of the few things standing between you and the botanical gardens, so I do appreciate it. Today, we are going to talk about machine learning in industrial control systems, specifically looking at what is currently present in academia, what is being published, and how that can actually turn into something useful. You may have seen any number of news articles, alarming deepfakes that get realer every day, many disastrous attempts at self-driving cars, or maybe you have concerns about the growing use of facial recognition in both the public and private spheres. And we will talk about none of these today because they're really not useful here. And if you think you have a use case for one of these in ICS, respectfully, you're wrong. There may, I'm sure, and there is certainly theoretical applications, but I would argue that there are much more useful and quite frankly much simpler applications of machine learning that can be useful here. But first, we're going to talk about a couple of the challenges, because there are some real challenges when bringing machine learning into an ICS environment. You might call them canal blocks. I know it was a year ago. It's fine. It's the ship that was in the canal. So the first is training data. If you're not familiar with machine learning, it is exactly what it sounds like. You are teaching a machine to learn something. You're giving the machine tools and data to have it learn something to achieve a task. To do that, you need lots of data. And I'm not talking just 5 days of logs. I'm not talking a month of logs. This graphic on the side is actually from a data set of SCADA traffic that you can use to do anomaly detection. And it is 16 gigabytes. It is multiple years of data. If one example we're going to keep coming back to, let's imagine a medical application. Let's say you want to know if a patient has tuberculosis. So let's say you have a data set that's a questionnaire. You know the person, age, height, weight, temperature, and then do you have a cough? Have you done a blood test? Have you done a skin test, right? You can't do that from 15 patients. You can't do it from 100, right? And then expect to go out and have that model hold up when looking at billions of people. When you're in ICS, you're also worried about sensitive information. This data set was published, for example, under multiple collaborations, to make sure that anything identifiable, anything potentially sensitive was scrubbed. But if you just pull data directly out of your EMS system, it's not going to be scrubbed, right? As some of my research, we had a couple of utilities partner with us to share some of their vulnerability management data. When it came to publish that, one of the conditions, and rightfully so, was that it was not identifiable. We did not share the data, and we did not publish the data. Now, did reviewers like that? No, they did not, right? But when you're using machine learning in an ICS environment and you're trying to get this training data, you do have to be sure that you're handling the information correctly. The third is feature selection. And again, if you're not familiar with machine learning, this may not be a term that you know. If we think about our case with this medical questionnaire looking at tuberculosis, right? Does a person's age tell you whether or not they're going to have tuberculosis? Kind of getting into statistics, independent, dependent variables. You can do the same thing when you're looking at what pieces of data are we going to use to train a machine learning model. These are complicated statistics, but they are doable. So I don't mean to scare you off of it, but you do have to take care and have the experience necessary to be able to choose appropriate features. If you choose too many, it's called a dimensionality problem, and it becomes computationally infeasible to train a model with that data. Machine learning is data preparation, and I don't say that to be blasé. You have to know both what is going into a model and what is coming out. And when I refer to a model, here's what I mean. Machine learning is an algorithm. It's just some math, and you apply data to the math. So if you have an equation that's like ax plus by, You put data in, and it figures out what A and B should be to get the desired result. You have to know what's going in, and you have to know what's coming out. As an output, do you want a yes or no answer? Is there attack? Is there an attack? Is there not an attack? Do you want a probability? Do you want it to predict if something is a flower, a dog, or a tree? You have to know how many things are you sending in, how many things are you sending out. That is part of the machine learning process. The second is specialized protocols, and I'm talking about Modbus. There are others, but really, and this kind of goes back to the training data problem. It's not that the protocols themselves are a problem. It's that getting appropriate training data for those protocols becomes that much more difficult when they are specialized, and especially when they are proprietary. If you're training a model on Ethernet data in ICS systems, and you need extra training data, especially data that is not malicious, right? And you can look at Ethernet data from many, many sources, and you will have an easier time generating what you need. With something like Modbus, that's going to be a lot harder. And the third is that we're in a real-time system, critical or not. When you're looking at models, you're looking at prediction times. How often are you going to predict? On how many samples will you predict at a time, right? Are you going to predict every second? Are you going to predict every hour? Are you going to predict every week? This matters. And when you're looking at a real-time system, these are choices that have to be made. So now that we've gone over challenges, first, not to scare you, let's get into some applications. So one of the main ones is intrusion and anomaly detection. If you this is from Google Scholar, not just from Google itself. So if you just Google like machine learning, SCADA, anomaly detection, I should have highlighted these, but you get about 18,000, and then for anomaly detection, and then intrusion detection, you get about 15.5. Okay, this is a huge amount of work, and while I cannot speak authoritatively, this is a vast majority of the work that seems to be done with ICS and machine learning. Everyone wants to be the person who creates the magic model that tells you exactly when something goes wrong and what is happening. However, when we consider what this actually looks like, the first thing we have to know is, are we looking at a system fault, or are we looking at malicious activity? They are different things, and like I said a minute ago, you have to know what's going in, and you have to know what's going out. Do you want the binary yes or no, attack or not? Do you want no, or yes, but there are categories? Yes, it's a DDoS attack. Yes, it's another malicious activity. Yes, it's a system fault, right? You have to know these things, and not just know them, you have to have the data so the model can learn them. How large of a data set could you produce of examples of system faults in your EMS system, right? This becomes a difficult problem. The second is anomaly incidents. How often do they occur? There's this great XKCD comic. It says, "Is it Christmas?" "No," with an asterisk. And the asterisk says, 99.6% accurate. Because if you guess no, you're going to be right most of the time, right? So when you're looking at something like anomaly detection or intrusion detection, things happen relatively rarely. You have to know the incidents at which it occurs. And you have to know what metrics to use. Accuracy is an easy one, right? It's the entire issue with the "is it Christmas?" No. You can be incredibly accurate and not be a good model at all. You can be incredibly accurate and not be useful. You have to know the statistics of your data and of the real world that you're working with. To be able to, you have to know what your baseline is. Your baseline for whether or not it's Christmas is 99.6%. You can only go up from there. There are other metrics like F1 scores that start to get into that a little more. But if someone comes to you with a model and they say, "Our accuracy is 99.9, you have more questions, or you should. And the third is prediction time, and this fits a little bit into those real-time systems. If you're going to look at intrusion detection, One of the benefits that so many of those papers tout is speed. But that speed only comes when you have the data at speeds to back it up. You have to be able to make all of this work, get the data out of your system through the machine learning, and use the predictions in a timely fashion. The second application is computer vision. So computer vision is you give a computer an image, and it tells you something about it. So maybe you give it an image, and it tells you what's in it. Maybe you give it a picture of a flower, and it tells you what type of flower. Or you give it a picture of a data center, and it tells you what's there. Now, this is not like ready to go, so please don't like call me when you're sad this isn't a thing yet. But there is some real research about using pictures of equipment, whether in a data center from a traditional server rack or something that you would find more in an ICS environment, and being able to get useful information from that. Now you may say, if I'm already in the environment to take a picture, is this really useful? And I would say, yes, because if it can give you a CSV with device numbers instead of you having to write each one of them down, I would say that's a pretty big benefit. Another one is state estimation. So most of my background is in power systems and the electric utilities, so you'll forgive me if I stay here for a little bit. When you're looking at state estimation, you're trying to get an idea of what's happening in the power grid at any state in time. And there's a inherent error that comes into this. You have the actual true state of the system, right? Your measuring devices inherently have some error that's introduced. The measurement is sent to the state estimator, which also, because of necessary computational shortcuts, will also introduce some error, and then you can get the estimated state. Using things like weighted least squares or calculations like that. There is some work attempting this with neural networks. Neural networks is a machine learning model created to mimic the human brain. You have a series of nodes that are supposed to be like neurons. They're connected, and they fire similar to the way neurons in the brain do. The two that I've listed right here, graph neural networks, GNNs, and convolutional neural networks, CNNs, both exploit locality. Convolutional neural networks exploit adjacency relations. So if you'll imagine an image, if you grab a pixel and that pixel is white, you might say, oh, okay, I should look at the neighbors. Maybe this is a cloud. Maybe the 8 neighbors surrounding me are also white. They're also part of this cloud. Or maybe they're white with a little bit of blue because we're blending back into the sky, right? This is how convolutional neural network works. It takes these adjacency relations and condenses those into a smaller representation. Graph neural networks also leverage connections, but instead of adjacent ones, it assumes a graph structure where you have nodes and vertices. So 2 nodes that may not be in a plane anywhere near each other can still have an edge with the same weight as 2 located very closely together. There's some new work representing power systems as a probabilistic graph, and we're not going to go into too much detail there. However, that work, only done, I believe, in 2019, has enabled the use of these graph neural networks to look at structures and relationships in the electric grid. We're going to talk about one more that, unfortunately, I don't have a slide for, which is vulnerability management. This is where some of my work comes in. Yes, I did forget a slide for my own research. This is what happens. With vulnerability management, it does get a little bit, this data problem gets a little bit easier because not all of it is sensitive. Now, when you look at the NVD, all of that's publicly available, and there are many of publicly available sources like ExploitDB, a number of sites where you can find information about this. There has been some success with exploit prediction, looking at what exploits that were publicly, like when they were publicly known, when was the vulnerability released, when was there a proof of concept, when was it seen in the wild. and using that historical data to potentially predict future exploits. Additionally, looking at, everyone wants to talk about how they're adjusting risk and how CVSS isn't ideal, and I will agree with that. It's not ideal. That's also an area where machine learning can fit in very well. So looking forward into what academia and what machine learning research can bring to ICS. One of the things that we're going to have to get there is realistic data. Now, I'm not saying, nor am I asking, for you to just share your data willy-nilly with any researcher who asks. There are real concerns and there are real ways to get there, nor am I advocating for another information sharing center. I will leave that to someone else. However, for example, the data sets available for intrusion and anomaly detection on SCADA systems inherently have flaws. They have shortcomings. That's just the way research works. And so the models that use them inherit those same shortcomings. Similarly, industry and academia collaboration. I've been very lucky over my career thus far to have taken part in a number of such collaborations. And I will say it's been very helpful. You can only research what you know, and you have to learn more by going and asking people. Now, I know I'm preaching to the choir. However, it is very, very useful. One of the last things here is practical solutions. Academics, especially academic conferences, love novel things. They want things to be new. They want things to be great. What they don't necessarily love is novel applications of existing solutions. That's one of the things that we've seen, and I'll admit has been my own frustration when you apply existing ideas to new applications, and it's not seen as novel. And so having something even like this, and I really appreciate the opportunity to come and speak about some of this, to talk about what's going on in academia. How do we apply things like neural networks, which have been around for quite a while? How do we take these quote-unquote simple or old machine learning ideas and fit them into an ICS environment? Not to bring in the latest and greatest and new, right? But to bring in technology that could actually be helpful, could actually relieve some of the burden of managing things in an ICS environment, and use them to actually improve the experience of those in it. That is what I have. I appreciate so much the opportunity to be here. And if there are any questions, I would be happy to take them.
First of all, I'd like to say I'm a huge fan of Janelle Shane's work, AI Weirdness. It
Yes.
illustrates your point exactly about
Yes.
Training the data set properly. I'm worried that the anomaly detection that you might use would be already in so many places that this would be yet another alarm saying, oh yeah, by the way, the AI has just decided that you've got a crazy thing happening. And it could be something dumb like, oh, I don't know, you're in a water utility and a transmission line breaks. You know, one of the really big ones, you know, like
Yes.
a very large pipeline. And the reason I point that out is because these are anomalies we don't see very often. And
Right.
when it happens, it drives us up a wall. So how do you keep this from causing the operators to just ignore it because, oh yeah, there it goes again. It noticed the pipe break. Yeah, I saw all the water tanks falling. That's easy for me to see. I don't need the AI to tell me that. You know?
Yeah, absolutely. And I think this is where there's two things here. One is that it cannot ever be a standalone system. Is that it has to be able to integrate, and not to sound like somebody up here trying to sell you something, but it has to be able to fit in with existing technologies with some kind of priority. There are things that will tell you if the transmission line breaks well before the machine learning algorithm will. And so there will have to be some sense in which there are sensors that will absolutely take precedence over what the machine learning might find. The other thing that I'll say comes into, it's the false positive rate and the false negative rate. How often, does something happen and the machine says everything's good, or everything's fine and the machine says, oh no. And that's some of those other metrics that I mentioned briefly, because a false positive is bad in a boy who cried wolf kind of way. A false negative is a potential disaster if there's something that is happening and it doesn't catch it. And so that's how, with some of this research, some of the other metrics that are looked at is how often do you have these false predictions, and how do you keep those rates as low as possible?
Right. I did work with AI back in the early 90s, and we submitted a tremendous amount of data, over a year and a half, to a bunch of researchers that were trying to build a neural network. And what we discovered, unfortunately, was that the chief plant operators and the chief distribution operator actually did a much better job at staying ahead of the system than the AI did. And the reason was because the data set wasn't big enough, and it didn't have the information like, is today a holiday, and what happens to the consumption curve when that happens?
Exactly.
So there's a question that always comes up is, what methods do you use? You say that we have this data set that we use to train it. How do you gather that data, and how do you train it up so that it doesn't false on you and do weird things like Janelle Shane likes to illustrate?
Oh, yeah, absolutely. Absolutely. And some of that comes in is deciding where the machine learning algorithm might be useful. And maybe it turns out that in anomaly detection is not an application where it is actually useful, because your operators have a much better intuition, and it requires such an overwhelming amount of data to train the model that it's not worth the time and effort.
Thank you.
Yeah, thank you.
Hey,
Hi.
I'm Arvind, and sometimes you got to put the attacker hat on. So with machine learning models, they're typically susceptible to adversarial perturbations. So how does that work with how do you work around that?
Yeah, and this is especially with some of the sensitivity. There's been some new research about how can you gain information about sensitive training data back out of the model. Some of that comes with open source is what I'm going to call it, being able to share the data that you trained on to let others evaluate it. There is certainly value in that, and so many, especially proprietary models, they won't share the data, they won't share the details, they won't share the configurations until you're stuck saying, okay, cool, you have a model that does this cool stuff, I can't know anything about it. Some of that, I think, has to come from pressure from customers and from market. I think as far as when you have a model in your system, I don't know that I necessarily have an answer to that. Besides other security practices, if you limit access to the model that you're using by the norm, like a good security posture, but it is absolutely an open question.
Thank you.
Thanks.
So maybe stretch out a little bit, and what's exciting and new in machine learning that you think will have implications? I mean, I'm kind of excited about reinforcement learning getting picked back up since neural networks had so much attention for so long. And then transfer learning seems to have a lot of applicability in this space, because when you start to talk about these problems, you start talking about huge data sets, and everybody says, oh, well, my system's a special snowflake. And it's like, well, yeah, there are specials in snowflake instances, but there are these like subsystems that we might be able to use a more broadly trained model for.
Yeah, and I'll say that some of the state estimation is what I'm excited about. There were some other papers that I looked at using transfer learning for this. The state estimation has been very similar for a long time, and I'm not someone to say no. I am someone to say don't break it if it works. However, some of the new approaches, especially with the increasing volume of data that is available, some of the calculations involved in state estimations do become infeasible, and so using some of these these new methods, like representing the grid as a probabilistic graph, opens up new doors to make those calculations better.
So one follow-up to that, I forgot to mention the first question. Like, we seem to have hit a plateau with image recognition in like that world for a while, and then the generative adversarial networks really were a breakthrough. Do you think there's an application for that here, where we're starved for data, for training data?
I don't know that I can speak definitively on that, and so I hesitate to speak to in too much detail. But I think that with the amount of data required to train some of these, especially anomaly and intrusion detection, well, I think there's going to have to be some application of that in this space.
What is the best way to evaluate a lot of these OT anomaly detection vendors? How to evaluate how well they do that? Is it just by simple proof of concept, or where do I start in order to evaluate these products if I want to purchase one?
Yeah, absolutely. I would say first, ask for their metrics. If you feel free to come find me, and I'll tell you more of them. Things like the F1 score, your false positive and your true positive rate, along with your accuracy, does become the first step in how do you start to tell if they actually work. Because if they just give you the accuracy and no more, to me that's a red flag, I'm just going to say. I would say ask for training data. I would say maybe they won't provide it, but maybe they will. Anything you can gain about, what did they train on, how did that go? Those would be my two first steps, but I'd be happy to talk about that more if you'd like. I think that's the end of my time, but thank you all so much, and have a great evening.